So hello and a very good evening to you all. So last problem solving session on Friday was shifted to today's evening because of some unavoidable circumstances. I welcome you all to the problem solving session 9 of the currently running course on manufacturing process technology. Today we will be discussing some problems out of the current week's content, and then we will be actually before that seeing at the assignment questions from the last week content, right? So let me share my screen for the assignment questions from last week. Okay. So yeah, going ahead, the first question was about the single crystal growth method, right? We have seen some problems out of single crystal growth method, and the theory had been taught to you during the regular classes. So the first question was about what is the crystal growth method that produces pure silicon crystals by dipping a seed crystal into a molten silicon bath. So from the process described, you can actually get that this is talking about the Zokalsky method, and and the question was, so Zokalsky's process is a crystal growth method that produces large and less pure silicon crystals by dipping a seed crystal into a molten silicon bath. So we discussed why the purity is less, right? So during taking the seed out, some of the extra molten metals get attached to that melt, and somehow it produces a less pure silicon crystal. So the Kralski's process is a crystal growth method that produces large and relatively less pure silicon crystals by dipping a seed crystal into a molten silicon bath, while the float zone method creates high purity silicon crystals by passing a molten zone through a silicon rod. So you can see the approach has changed, right? Resulting in significantly less impurities due to the lack of direct crucible contact, right? So the next question was lithography, about lithography. So whether lithography is an additive or subtractive process. So lithography is an additive process as the material is being added to a surface by selectively exposing specific areas initially coated with resist layers to create a desired pattern. Okay. So we saw the lithography process through a schematic very elaborately in on last class. So this question wouldn't have been quite tough for you to answer, right? The next question was about a physical dry etching process. So you know how physical dry etching happens. It happens to bombardment of ions, electrons, and photons onto the substrate surface, right? There is nothing about etchant liquids or etchant gases. So the option B was the correct option here. Then there was a simple question about lithography process. So if you clearly know the process of lithography, you might be knowing that lithography process, the resolution actually depends upon the wavelength of light and then the distance between the substrate and the hard mask, right? So here lambda stands for the wavelength and S stands for the distance between the substrate and the hard mask. So using this simple constant, you get this formulation from which you can guess it that for lithography, this formula provides the resolution of lithography process where lambda and S are the wavelength and distance between hard mask and the photoresist layer. The next question was about which type of uh, photoresist is being used for getting the features in option 1 and option 2. So we have seen how a positive photolithography process differs from a negative photolithography process depending upon the tone of the photoresist. So in the first case, you know that you can see the exposed areas are being washed away after developing process. So that means that there is cross connections, cross linking process happening in the unexposed areas. So that you know is an indication of a positive photolithography process. And the second case is the reverse one, which is a negative photolithography process. So what happens is in positive, light will weaken the resist and create a hole. Yeah, so the exposed parts gets washed away once you develop that is the developer solution. While in the negative case, light will toughen the resist and create an etch resistant mask in case of the exposed areas. Okay, so you are getting this negative of the pattern in the first case. So this is a negative photolithography process and the negative photoresist is being used in option 2. So if you look at the choices given, option A becomes the correct answer. Question number 6 was about a negative tone photoresist while so PMMA, PDMS is is not a photolithography material, it is not a photoresist. And so upon PMMA is not a photoresist, so SU it's a photoresist. So the first one automatically is clear choice, that is SU8 is a negative tone photoresist, while PMMA is a positive tone photoresist. So negative tone photoresist is only SU8. So in the option C and D you have SU8. So if you go and select the next blank, so PMMA becomes a positive tone photoresist. So the next question was about dry etching process, which has a very high precision. It is an ultra precision manufacturing etching process as compared to wet etching, which use liquid etchants. Okay? So option B was the correct option here. And then there is a question about etch selectivity. We have seen through some diagrams how etch selectivity, what etch selectivity is, and what defines etch selectivity, and how important it is in case of micromachining processes. So high etch selectivity is necessary characteristic in micromachining for low substrate damage. So given there is a high etch selectivity, substrate damage comes down. Given there is a low selectivity, the substrate damage goes up. So option C is the correct option clearly. Then you have a question about full form of MEMS. So you know that MEMS is all about systems and micro electromechanical systems. Option 1 is a clear and easy answer here. Find the resolution of lithography process if wavelength is given and the distance is given. So just the formulation we have seen in question above. So it was a cakewalk for you. Resolution of lithography can be found out by this formula, B equal to 1.5 in bracket multiplication of the wavelength and the distance between mask and substrate surface, and then raised to the power of half. Okay, so just plug in the values and you can get the B value as 0.043 millimeters. So this much concludes your last week assignment questions. If you have any doubt, you can shoot up. Otherwise, we'll move ahead and check some problems out of the current week's topic. Okay. So, considering that you are done with your doubts, so we'll start with discussing some of our problems from the current week's content. Okay. So I hope you can see my screen, and in that case, let's start with a concept called mass loss of workpiece. Okay, something like that is seen when there are abrasives hitting the surface in case of abrasive jet machining. Okay, so generally the concept is the abrasive hits the surface and then there is some incubation period after which the erosion starts related to the velocity of the particles. Right? That's empirically. However, theoretically, there is also a dependence upon the ratio of density to hardness of the workpiece and the kinetic energies of the abrasive. All right. So here you can see the formulation for mass loss of workpiece where K is called as the velocity coefficient, which is a dimensionless factor, and the values varies between 2.3 to 3, found out empirically in case of metals. Okay. In case of glasses, the value varies from 2 to 4, and in case of elastomers, the value varies from 1.8 to 3.2. Okay. So here density and hardness of the eroded metal are just shown through rho and h. Okay, and half mv square denotes the kinetic energy of the abrasive particles. So the above relation is true for brittle erosion, but not for softer materials, elastomers, and some metals due to time variant erosion behavior. Okay. Especially at normal impact angle, the particles tend to embed in the material, resulting in an initial gain in weight of the specimen. After this incubation period, steady-state erosion starts, and mass loss from the eroded material is proportional to the amount of abrasive particles. Then the principal empirical relation between the erosion rate, E rate, expressed as the quotient of mass loss and amount of abrasive and particle velocity, is given as a power function by E rate almost equal to V raised to the power K. Okay. So given that, let's look at one question. Suppose you are actually given a metal mask, all right, which is of 100 micron thickness. So a hole pattern is there just to be transferred into the substrate through this mask. The hole is 80 microns of diameter. Okay. And then there is the glass specimen in which you have to cut out the micro hole. The glass specimen is of dimensions 250 cross 250 cross 1.2 millimeters cube. Air pressure is 2 megapascals and velocity of the steam is 150 meters per second. Density of aluminum you can take as 3950 kg per meter cube, and density of abrasive you can take as 2500 kg per meter cube. So here are some more data. The hardness of the eroded material 585 10 raised to the power 6, and feed rate of aluminum abrasives is 0.02 gram per second. So by now you know the formulation, how the mass loss varies. Okay, so actually that is the weight loss which you are talking about. You just have to find out the mass loss from this from this. So K is the velocity coefficient, density by hardness factor of workpiece multiplied by kinetic energy of the incoming abrasive particles. So this combination of multiplication of these three gives you the weight loss. So just give it a try to solve this question, and then we will go ahead and see the solution. Hope you have tried. Let's look at the solution. We have just seen how the mass loss or weight loss actually varies uh, with the density to hardness of the workpiece ratio, as well as the kinetic energy of the incoming particles, other than the velocity coefficient k. So in case of metals, you know that k varies as uh, 2.3 to 3, right? It's a constant value. So let's take the value of k metal as 3, and the density to hardness ratio you can find out because these are already given for soda lime in the question. So okay, and then uh, the kinetic energy you can find out by finding out the mass value because velocity is already given. Okay, so now the question becomes how to find out the mass, okay, of the grains. So m, the amount of the abrasive particles in kg, so volume of the hole multiplied by the density of alumina can actually give you the amount of abrasive particles, right? So volume of the hole, again you can find out by multiplying the area into the depth of the hole, and here pi r square becomes a spherical the circular area of the hole, and multiplied by 1200 microns, because 1200 microns has been uh, actually the depth of the depth just to be carved out in the glass specimen. So 1.2 millimeters is giving around 1200 microns, right? So density of alumina is also given in your question. So density of alumina is nothing but 3950 kg per meter cube. So plugging in all these values, you can find out the mass, and then the mass loss you can find out by weight loss, dividing that by gravity g. Okay, so just plugging in the value of the mass, you can find out the weight loss using this formulation, and when you divide that with the gravity, you can find out the mass loss as 0.34 multiplied by 10 to the power minus 9 kg. Okay, the time required then becomes the mass loss divided by feed rate. If you look at the units, the mass loss is in kg and feed rate is in kg per second. So in that case, only the unit becomes seconds. So the time required can be found out as the mass loss dividing that with the feed rate value. Okay, so hope you got this question. Just take a note of it, and then we will cross it to find one more such question out of implicit jet machining process. Let's move to the next question then. Um, before talking about that, let's talk about two concepts called as mixing ratio and mass ratio in case of abrasive jet machining, abrasive water jet machining, maybe. So here you have the mixing ratio as the volume of abrasives to the volume of gases or maybe water in case of water jet machining. Okay, and then the mass ratio is again given by the mass flow rate or mass of abrasives to the mass of total mass. Okay, that is abrasives plus the gas or fluid, whatever it is there. Okay, so suppose we have a question in which you have been given the mixing ratio as 0.3. You have to find out the mass ratio given the ratio of density of abrasives to density of gas is 15. So a very easy concept. Just have to reshuffle the equation where you just have to replace a mass of abrasives as a product of velocity, volume, and density. Okay. So the numerator here becomes the multiplication of product of volume into density of abrasives, and the denominator becomes uh, the summation of the product of abrasives to and density and volume of abrasives to density and volume of gases. Okay. Just reshuffle them to find 1 upon 1 plus Vg rho g upon Va rho a. Okay, and just you have to plug in the values. So for Vg upon Va, you can find it from the mixing ratio value, it is 0.3, so it is 1 by 0.3 and multiplied by rho g upon rho a, which is 1 by 15. All right, so the mass ratio then you can find out is to be 0.82. So I hope this kind of problems, if it comes in your assignments or exams, you can solve it out and just take a note of it, and then we'll look to some problems out of ultrasonic machining processes. So proceeding ahead, let's see one question of ultrasonic machining. Okay, so I'm not going to the derivations and formulations. You know all those things from your regular class lectures. Let us take an slightly twisted questions in which the shape of the hole to be actually machined is a polygonal shape. It is a hexagon of side dimension 5 millimeters, and the thickness which has to be inscribed is 4 millimeters. Okay? So now the dia of the abrasive grains are given to a 0.1 millimeter, and the force of the tool on the grains is 3.5 newtons. Then you have the amplitude of the tool is 25 microns, and the frequency, which you know is also an important parameter in ultrasonic machining process, is 25 kilohertz. Hardness of the workpiece is given as 6900 Newton per millimeter square, and the fracture hardness of tungsten carbide, which is taken out to be the material of the workpiece. You have to determine the time required to get the hole. Okay? So just give it a try, and then we will look into the solution. So let's look at the solution now. I hope you have given it a try. So this is a hexagon. What you can do is, so you have to find the area. You have to find the volume. So you have to find the area first. You can divide an hexagon. How to find the area of a hexagon? You can divide the hexagon into 6 different equilateral triangles, right? And then you know how to find out the area. If you know how to find out the area of an equilateral triangle, then the total area can be found out by multiplying the area of each equilateral triangle into 6. All right, so 4 multiplied by root 3 by 4 and the side squared, it gives the area of an equilateral triangle. So if you multiply it by 6, you get around 2129 millimeters square. So the next question is, in case of ultrasonic machining, so if you take a grid dia to be D, the question is the whether it is a perfect sphere. No, it is not a perfect sphere. The grain is never a perfect sphere. So to accommodate that, empirically, it has been concluded that let's take the square of whatever dia we are getting. So here in this problem, if you can, in the diagram, you can see this is the grain, okay, and dia of the radius of the grid is d1 by 2, okay, d by 2. So then d1 becomes equal to d square. You have to take the square of whatever die will given. So d1 is equal to d square. It is equal to 0.01 square 10 to the power minus 4 millimeters. Right? And then the number of particles, okay, that can be found out by three factors. First one is the ratio, the concentration of the particles in the solution, okay, multiplied by this factor, which is the area, all right, of the particular uh, hole which is to be inscribed, and divided upon the area of one grid. Okay, considering this to be a sphere, we can actually find out the number of particles. So we have found out the dia, we have found out the volume of the hole to be inscribed. We have also found out the number of particles. Right. So now the next question is how to find out the indentation depth, HW. Okay. So that is given by the square root of 8 into force of tool on the particles multiplied by amplitude of the tool, and the whole product being divided by pi of d1 squared. So by now you know why we considered d1 multiplied by the number of particles z, and then the hardness of the workpiece hw, and then the multiplication of 1 plus lambda. So lambda in this case is the ratio of hardness of workpiece to hardness of the tool. Okay, so let us assume that we 5. So the total Q or MRR becomes 2 by 3 pi d by 2 of cube of that multiplied by z, and then the frequency of the tool motion nu. So what is D? So D is the indentation depth. Okay, so here you can see that suppose, so here we are talking about indentation height. So now we are talking about indentation depth. So D being the capital D being the indentation depth. So let's find that out in terms of D1, small d1, which is the effective dia of indent, effective dia of a grid. Okay, and then you have the small hw, which is the indentation height. Okay, so using that, you can find out the total depth of indentation is twice of root of d1 hw upon so by 2, as the whole thing cubed and multiplied by z and nu gives you the value of mrrq. Okay, so the question was to find out the time required to get the whole. So if you have calculated the MRR, if you divide the total volume of material removed by the material removed per unit of time, you can actually get the time value. So you can, if you know the steps, if you have understood the steps, you can calculate it to get the total value here. So you can take a note of it, and then we'll move to the next question. Or if you have any doubts, please you can ask me. Okay, then let's move to the next topic. Here is just an extension of the earlier problem. Again from USM, here the tool is changed from copper to stainless steel, and you have been asked to determine the percentage reduction in the time of machining. So by now you know M error is inversely proportional to 1 plus lambda of 3 by 4. Okay, that you can see from simply the derivations. Okay, so if you know that, then you just have to find out the ratio of QC upon QS. So QC is the ratio between QC is the MRR in case of copper, okay, and QS with MRR in case of steel. All right, so then because this is inversely proportional, so you have that equals to 1 plus lambda s which is the ratio of hardness of workpiece to the hardness of the uh, so here lambda is the ratio of hardness of workpiece to lambda the hardness of the tool, right? So just plug in, you can plug in the values here. So 1 plus lambda s upon 3 by 4 divided by 1 plus lambda c upon 3 by 4, which then equates to lambda s almost approximately lambda s upon lambda c whole to the power 3 by 4. Okay, that again may equate to the hardness of copper, actually to the hardness of steel to the power 3 by 4. So you know that copper is a very soft material, it is a very ductile material, and the hardness is almost 1/3 that of steel. So just plugging in the value, you can find that 1 by 3 upon 3 by 4 is what is the ratio of QC upon QS. Now, because higher the MRRs, lower will be the time required to complete the machining process. So TC upon TS becomes the inverse of QS upon QC, which is 3 upon 3 by 4, which is almost equal to 2.27. Right? The percentage reduction in machining time then becomes close to 56%. So I have a note of this, and then we will move to our next question. The study materials anyways will be shared to you over a Google Drive link. I hope then you can access them easily to just refer to these materials later on after we are done with the classes. If you have any doubts, you can please ask me now. Okay, so let's move and look at some of the concepts out of ultrasonic machining process. Something called as crushing of grains during ultrasonic machining. So here I have given you the equation for finding out the MRR in case of USM, which is 2 by 3 pi of twice square root of D1 HW. D1 you know is the effective uh, dia of the grain, okay, or the grit, and then HW, okay, is the indentation height, okay, and then and then this divided upon 2, and then the whole thing cubed multiplied with the number of particles striking and the frequency of the machine tool. Okay, so from that you can derive that Q in case of USM is actually proportional to D1 raised to the power 3 by 2, right? So ideally what had to happen is the MRR should go on increasing with increasing the main grain diameter. So in the x-axis, you have the main grain dia D. In the ordinate, you have the MRR Q. So theoretically, the Q or M error should have gone on increasing with increasing grain dia, because it is almost proportional, directly proportional to d1 raised to the power of 1.5. But that doesn't happen in actuality, and it goes on decreasing after a particular point. So why does that happen? That happens due to the crushing of grains after a particular time interval in USM. So if you are asked about this, you just have to have in mind why these things happen. This is because of crushing of grains during a USM. One more thing is about the feed force. So the force of the tool on the workpiece. Okay, so the Q is again proportional to F to the power 3 by 4. Okay, in that case, you have a parabolic curve. All right, you have a parabolic curve which goes on increasing first and then plateaus and then goes on decreasing. Okay? So, but actually, after a particular point, it goes on decreasing more rapidly than what it should have happened theoretically. So, Q actual is the blue line. You can see it is the slope is gradually falling down with increasing force by the tool on the USM grains. So why does that happen? That is again because of the crushing phenomena. The accumulation of grains actually leads to grain crushing by the tool with increasing force, and that leads to reduction in MRR process. Okay, because there is no effective material removal by the grains, crushed grains. So these are some concepts I wanted to discuss with you, and then we will finally move to the last question. Okay, which comes from abrasive water jet machining process. Uh, just try to take a note of these points, and then we will take up the last question. So here we are talking about abrasive water jet machining. You have been asked that if the diameter is doubled of the grains, what effect will it have on the MRR, okay, material removal rate? So let's look at how to go to that solution. So in case of abrasive water jet machining, let's first find out the MRR value. Similar to the other processes, we can equate the kinetic energy of the grease to plastic strain energy of the workpiece. So kinetic energy you know is given by half mv square, mass and velocity mv of the grease particles, and then plastic strain energy is half of the average of the total force F max and multiplied by the height of indentation or HW. Okay, so then you have the half of density multiplied by pi d cube by 6. So this is giving you the total mass, and then the velocity squared equal to half of pi d square by 4 multiplied by sigma stress, which is almost equal to hardness of the workpiece, okay, multiplied by the depth of indentation. This is equal to twice square root of d hw, you know that, and this is equal to the height of indentation multiplied by the dia of indentation. So that is dia of grain, which is actually giving you the total uh, indent dia. Okay. So from that you can find HW is equal to square root of rho by 6 times hardness of the workpiece multiplied by velocity into the dia of grade D. So Q, the total MRR then becomes volume removal uh, per cycle multiplied by the number of impacts. So uh, considering this is an hemispherical indent into the workpiece, the total volume removal can then become 2 by 3 pi of r cube or d by 2 cube, okay, multiplied by d is the indent dia, and then you have mass flow rate upon density rho multiplied by pi by 6 pi d cube by 6, which is actually giving you the total number of impacts. So the denominator you have the volume, you have the total mass, and then you have the mass flow rate. That is the total number of mass flow per unit time. So there you can get the number of impacts. And using that MRR value, you can simplify it to find out that the MRR actually is directly proportional to the grid dia cube of that. Okay, so the question was, what happens if the dia is doubled? Okay, so that because it is varying directly to the cube of the dia, you can have the ratio as the new MRR to the old MRR as 8 times. Okay, so the new MRR becomes 8 times with the old MRR by doubling of the grid dia. So that was how that is how we I'd like to conclude today's problem solving session. I'll leave it upon you to take the note, and if you have any doubts, you can go ahead and ask me. Okay, thank you.